Hi, in this video I wanted to talk about number 10 on section 4.4 homework. This one has some questions, and just in general, let's talk about derivatives of exponential functions and their applications. So here we have a compound interest equation. If you remember from college algebra how we get that, 4,000 is the initial amount. And then this is the continuous interest. It's E times the rate, which is 5%, or we call it 0.05 in the decimal form, times T. So the first thing we need is the formula for the derivative. Let's review this real quick. Typically how I teach this is we keep the initial amount, 4,000. It's like a constant multiple rule here. So we keep that 4,000 times the exponential itself. We're focusing on chain rule here from this section 4.3, I believe. So it's the exponential. We're not subtracting anything. It's not the it's not like polynomials where we subtract 1, but it's itself e to the 0.05t. Notice how it's not changed, times the derivative of the exponent, which in this case is just 0.05. So what we end up multiplying is the initial coefficient or constant, 4,000, times the derivative of the exponent, which is 0.05. So that's how we get the 200 e to the 0.05t. I happened to check this portion already, so hopefully you guys had easier time with this one. Now, let's be careful how we plug in 8. We need to plug this into the derivative, and again, it depends on how you have your calculator set up. But I basically put in 200 e to the, let's take a look right here. Okay, so here I have the graphing calculator. So we have 200, and then to locate the e, it's second ln. And mine shows up with the exponent. Otherwise, you may want to use parentheses. So I put 0.05 times 8. And let's enter. And I'm getting 298.36 and so on. Let's take this down. And it says round to the nearest dollar, so I put 298. Now here we had several choices. The one, let's talk about this. Remember, the derivative is the rate, so something is changing per something, okay? So it's definitely not just dollars, and it's not just year. It's not the time that's changing. We do know it's dollars changing, so it's definitely between the first choice and the second choice. But let's read them carefully. So dollars increased in the total amount per yearly increase in the investment period. It sounds like a mouthful, but dollars increased. Yes, that's what's it's positive rate, so it's dollars is being increased in the total amount per, that means divided by yearly increase, and that's the change over time. And it is change over time. Notice how it's dA over dt. Sounds like the first choice is the correct one. The last one is dollars increased in the total amount per dollar increase. They do not even mention the time, so it doesn't sound like the rate. So it's definitely the first one. And we check the answer. Yep, and it is correct. Now let's read through these carefully. Again, let's remember this is very similar to the marginal quantity, marginal cost, revenue, etc. So let's see. The future value of an 8-year investment of 4,001 will be more than the future value of 4,000. No, that doesn't sound quite right. So now here we're talking about, we plug in 8, but remember the marginal quantity, we're actually checking the approximate amount of the next year or the next item. So we're actually adding +1. So if you plug in an 8 into the derivative, you're actually approximating the future value of a 9-year. So here you have a couple of 8-year. Nope, that's not correct. You would have plugged in 7 if that was the case. So it's definitely either C or D, and we're going to have to read carefully. Okay, so the future value of a 9-year investment of 4,000 will be the blank dollars more than the future value of an 8-year investment of 4,000. This sounds about right. Now 4,001, here they're kind of trying to trick us to add the 1 to the amount, but that's not quite correct. It could have been the next year, but not the amount. I'm thinking it should be part C. So that's the initial amount of 4,000, but it says the future value of a 9-year investment more than the future value of an 8-year investment. Remember, it's like one value of one more item, cost of one more item. In this case, it's the value of investment of one more year. And here we put in the amount of $298 because this is the increase. So that's what the derivative tells us, by how much it increased from one year to the next. So let's check the answer. Hopefully it's correct. Yep, it is correct. Good, well done. Okay, now the next step is, this is similar to your group project, I think for the number 1. We are comparing the exact cost, the exact increase of the investment versus the approximate. So the derivative gives us an approximation. This is the way to calculate the exact, because A of 9, if you plug in 9 into the original investment equation, would give us the total for the whole 9 years. If we plug in 8, it'll give us investment for the whole 8 years. So if we subtract both of them, we just get the 9th year, which is what the derivative is helping us to approximate. So let's bring up our calculator right here. And let's calculate in the original equation, which is 4,000. And then second ln e to the 0.05 times 9. Notice how I don't even use parentheses because otherwise it might be off. I don't think it would be wrong, but let's not worry about it. So then minus 4,000 second ln 0.05 times 8. So notice how I am plugging into the original equations, enter, and here we're getting 305.95, it looks like. Let's see how much we have to round it. Round to the 2 decimal places. Let me make sure I'm typing this correct. 305.95. 305.95. Hopefully we're getting this right. I know it can be nerve-wracking. And yes, we did get this correct. So let me pause this. So did you notice what we did here? Now, the 298 was the approximation given by the derivative, but the exact change was actually a little bit higher than that. Sounds like about $7-8 higher, something like that. Almost $8 higher, but still it's fairly close. So sometimes the derivative gives us really close amount, and sometimes it's a little bit off. Like with exponentials, the exact amount is actually even a little bit higher, which is good maybe to underestimate how much your investment increases rather than overestimate. So maybe that's a good idea. So again, let's review what we did here. We found the rate of change is the derivative, okay? By keeping the constant, keeping the exponential the same, but then multiplying at the end by the derivative of the exponent. And so that's how we got the 200. Then we plug in 8 into the derivative to figure out how much does the investment increase from the 8th year to the 9th year. We're trying to approximate 1 year ahead in this case, or like with marginal cost would be one more item, and so on. Okay, so we got $298. And again, this was the rate, so it's dollars increase per yearly increase, because it's the rate, so it's dollars per year. That's really all it's saying, the dollars per year. And that's the amount of increase again. Now, the choices here, the 8th would not have been correct because we're talking about 1 year ahead. So here we have the future value of a 9 year. And again, we're talking about the initial investment, 4,000, that does not increase by $1, like it seems right here. And it would be 298 more. I think part C is the only correct answer here. And again, in the last question, we are comparing to the exact increase. And this is something similar you're going to be doing in number 1 in the group project for this week. This is how you can compare to the exact cost of the commercial. You can plug it into the original equation and subtract. Because again, when we plug in 9, we get the whole 9 years of interest versus 8, the whole 8 years of interest. And when you subtract the 2, you only get the 9th year investment, which is what the derivative gives us directly. Okay, so this is how you can compare the two. And that's it.